In this lecture video, we're going to talk about how to design logic. Now, a lot of this is an art, and it takes some intuition and some rationale behind how we actually solve algorithmic problems. Now, as you see, as we transition into this new phase of designing problem solving, you'll see that instead of actually saying, here's the string, do something with it, here's this data type, do something with it, here's some Python, do something with it, instead you're given a problem in a word problem form, as if your boss came up to you and said, hey, look, I've got these trucks, we need to do something with these. And a lot of companies like Google, Facebook, Netflix, and stuff like that, whenever they're quizzing project managers and things like that, that's the sort of thing that they're giving them. During interviews, coding tech interviews, that sort of stuff, they will give you a problem like this. For the project managers, they want to see, okay, how would you design the project around these? For the coders, they want to see, okay, how would you design the Python around this so that it actually functions properly? So learning how to actually design logic takes experience. That's why a lot of these problems are fairly straightforward, fairly simple. And I don't want to insult your intelligence or anything like that, but as you gain more intuition, you'll see how simple these problems really are. Wrapping your head around something takes some time to actually understand what's going on because you're new to Python, you're new to this coding algorithms type of thing. So it's going to take some time before you feel comfortable doing it. In fact, there's a lot of problems that are out there. That's why they pay computer scientists a lot of money, because developing the algorithms is the challenging portion of this. This is the challenge. This is where all that you've learned for the first half of the class actually comes into play. This is why we're here, to be able to solve problems in your respective fields. If you're an industrial engineer, it's going to take knowing how to use the Python in your career field to be able to use it correctly. If you're in physics or mathematics or mechanical or civil engineering, you have to be able to orient your problem towards Python. I don't know. I'm a computer scientist myself, so I don't know how your problems will actually stack up against Python. I do know that a lot of you are using Python in your respective fields because of the power that it gives you. So let's go ahead and start with this lecture. Designing an algorithm that is both efficient and useful. So there are two different things that we're looking at here. Number one, is it useful? Does it actually solve the problem, and does it solve it completely? Number two, is it efficient? If it takes me 15 days to solve a problem and I only have 7 days, then it's not that useful. Some things require a supercomputer. In fact, we have Titan, Kraken, and all these different supercomputers that are required to model certain high-level physics algorithms, mathematical algorithms, and things like that. But this is why programmers get paid the big bucks. If you have programming experience and you know how to solve a problem, even if it's just a little bit like you're learning in this class, you are that much ahead of your peers. So I call this an art. In fact, the course says the art of programming is where you take your combined knowledge and you sort of massage it into the problem. As you saw with Python, as you saw with the way I write Python, versus the way it's in the textbook, versus the way it's in the lecture notes, versus the way it's in the video, there are several different ways you can do the same thing with Python. Some have different efficiencies than other, but that's up to you to discover, okay, given this problem, do I have 15 days to run this, or however long it's going to take to run it? With the simple algorithm problems that we're doing now, it's instantaneous. However, that's not always going to be the case as your data sets get increased, and increased. So one thing that I've been doing with these algorithm problems is you'll notice they're word problems. In fact, they're not even speaking like a program at all. It just says, write a program that solves this issue. Now, there are some restrictions, some constraints so that our testing platform can actually test your program. But the main purpose of this is to make sure that you design something around somebody who doesn't know about programming. So when you get to your unit or to your business or wherever you're going to start working, or academia, whatever it happens to be, someone's going to be like, what is Python? And you're going to be the expert in your field. So you'll have to be able to take their requirements, which are just paragraphs after paragraphs or spoken words, and develop an algorithm with it. So I've developed I've developed 5 steps to help you generate an algorithm based on constraints. So I break down a problem 5 different ways. There are many different problem-solving techniques that you can use to help break down a problem, but these 5 I found work for me. They may work for you. If they don't work for you, there's other problem solving techniques out there. In fact, your career field or your major might have different ways to go about these. I'm not saying this is the right way. I'm just saying that this helps bracket out an algorithm. And you'll see whenever I do the solution videos on your algorithm problems, that's what I'm doing. I'm incrementally programming these using these steps. So number one, break out the design must-haves versus like-to-haves. One of the things is always set yourselves a goal. This sounds dumb because you only have so much time to actually do this, but you need to be able to budget your time so that you know, okay, we must have this. If without this section of code, I cannot solve the problem, versus like-to-haves, like where I make the interface nice and pretty and stuff like that. It's not a requirement. I can just spit out a number and I understand what that means. So getting the core requirements done are more important than the should-haves. That way there, if you have enough time after your must-haves are done, then you can go and do the like-to-haves. You can start massaging your program and start seeing how, okay, let's make it better, make it better, make it better. But developing that core so that you at least have something to visualize, something, I give it inputs, it processing, I have some sort of outputs. That's what's important, because a lot of times it's very difficult to see the end result unless it's there. So that always develop the small core of must-haves and then start working around it, massaging it so that you have all these other things that make it look like a better program. So that's number one. Mission creep or what is known as scope creep is a real thing. All of a sudden they say, oh, well, you finished it within 3 days, but you have 7 days to do it. So you have 4 more days to start adding stuff on top of it. However, for a program to be designed efficiently, you have to start off with the design. Modifying code after it's been designed, after it's been developed, is much more difficult than designing it right from the start. So if you find yourself doing mission creep or scope creep, there's 2 things you have to do. Number one, you didn't design it right off the bat the right way. Or number 2, someone's trying to add constraints or add features to your program that may not fit with that program. It might be time to write a new program should that happen. So we're actually going to work a little bit backwards the way Python runs. Number one is determine the must-haves versus like-to-haves. Number 2 is determine the outputs. So one of the things is most programs follow a general flow of inputs. So the user inputs something, we process those inputs, and we output something. So that's generally how a program is going to flow. But we sort of do it backwards because the end result is the outputs. We want to know what these outputs are. And so without knowing what the outputs are, we don't know what to input and we don't know what to process. So that's why it seems like it's a little bit backwards from the way the program actually runs. So determine the outputs. Write down what the goal of this program is. What do we want spat out whenever we're done with all this? Because you could process, you can input all this data, and it doesn't matter if it doesn't result in the output that you're looking for. So the next thing you want to do is analyze the inputs. So given this output, what are sort of the inputs? And notice we're sort of creating a sandwich. We have our outputs at the bottom, our inputs at the top. However, we're sort of going backwards. We figure out what our outputs are. That way there we know what inputs we need to input. And that's where the intuition comes from. Based on what the problem is, okay, what sort of inputs do I need to be able to produce these outputs? We don't actually have to calculate the numbers yet. That's the next step. But we have to figure out, okay, to get this output, what do I need? For example, if I want to get the length of a line or something like that, okay, well, I need the starting point, the ending point. I need both endpoints, and I need to calculate the length. And so those are the sort of things that you need. What is the output? Based on that output, then you can figure out what the inputs are going to be. Okay, after you do that, you need to orient your problem to your environment. So we've determined what we must have, the central core of the program that we want. We've determined the outputs that are going to come out of this, and we've determined the inputs. So now what we have to do is we have to say, okay, how are we going to, number one, get these inputs? And number 2, how are we going to spit these out? And so orienting the problem to your environment is basically saying, okay, what sort of system are we going to use to actually solve this problem? Now, in this class, we use Python, but that might not be it. You might use MATLAB. You might use all these other things, C++, other programming languages to actually solve the problem. In this class, like I said, we use Python, so you have to orient all of this stuff around Python. Remember, we input things using input in Python. That's not the same with MATLAB. That's not the same with C++. So our different ways to get input from those different languages, those different environments. But for this environment, we know that whenever we input something, it's going to be a string, and then we can sort of orient those inputs by either converting them to integers, floats, or whatever it has to be. And you know, that's sort of what the first half of the class was, orienting you to Python. How do we do these things in Python? Now you're actually using what you've learned to actually solve the problems. That's the main reason for this. One of the biggest steps I wish I can employ, I wish I could just open your brain and shove this in there, is solve the problem incrementally. A lot of students, even I did this, is you just sit down and you start writing from first line to end line without any goal in mind. You just say, okay, I just start writing things, and you click compile, you click run, you click run, you click run, you click run, and you just start fixing your errors as it clicks run. You don't get the right results, so you just keep, there's no strategy involved. You need a strategy to be able to solve this, or you're just going to waste time figuring out, well, I couldn't get that to work. So solve the program incrementally. When you watch the videos of me solving the problems that you're doing, you'll notice that I write a little bit, test, write a little bit more, test, write a little bit more, test. And that is how you solve incrementally. If you do it right the first time and then add a little bit more on, if you write the entire program, now you have to debug the entire program. Everything from top to bottom now could have errors in it because you never tested it. But if I test this little section and then this little section, now after those two are done and good, now I just have to, now I can narrow down the bug into a smaller section. So that is going to be the most important thing that you can do. If you take away nothing from this lecture, solve the program incrementally is going to be the important part. So those are the 5. So just to review, number 1, break out the design into must-haves and like-to-haves, determine the outputs, analyze the inputs, orient the problem to your environment, in this case Python, and then solve the problem incrementally. That's going to be extraordinarily important whenever you go through this. Even with these simple programs, you'll see that if you write a little bit, test, and you'll notice what I do inside of the algorithm solving problems is I'll print out the intermediate results. Now, maybe we just want one integer printed out, but I'll print out the intermediate results like a list to make sure the list contains the elements that I expect it to have, that I make sure that the list is, I just sanity check and say, yep, there we go. That's exactly what I expected it to be. If it's not what you expect it to be, you can debug that just a little bit of code and figure out why it wasn't that way, and then solve that incrementally. That's what we mean. Solve a little problem, tiny bit, a small section of that core problem, print out the intermediate results, see if it makes sense. So let's do a little bit of, well, before I get to there, let's talk about working with bugs. Bugs are going to happen. I cannot write a program without a bug in it. That's complicated. So I have an operating system that I have inside of here that I show you, but bugs do occur. We're all human. We all make mistakes. It's like a mathematical error. Even when I got my PhD, I still make sometimes arithmetic errors. You know, I'll do like 16 plus 12 and be like, okay, that makes sense. We've done it over and over and over again. That is second nature, but still writing something down, my hands do something different than my brain. And so bugs are going to happen. If we solve incrementally, we can solve bugs in small sections of code rather than the entire code itself. So bugs are going to happen. There are 3 different types of errors that we can get inside of Python. Number 1 is called a syntax error. Now let me go over to here and show you what a syntax error looks like. So syntax error is basically Python looks at it and says, I don't understand what you're trying to make me do. So let's say A equals 12. Let's see, B equals A. And I'm just going to put in an operator that doesn't exist, $17, $17, okay? So $sign is not an operator that we learned. It has no idea what $sign is. So as you can see, what we've gotten is a syntax error. Python's like, I don't know what you want me to do. So that's a syntax error. Notice that the program doesn't even run. And in fact, tells me, go to line 3 and fix this. Okay, so that is what's known as a syntax error. The second type is called a runtime error. That means Python, everything is known to Python. It's trying to do what it does, but it's only at runtime where it doesn't work. For example, if I create a list, 1, 2, 3, and I do A sub 10 equals 20. Now, obviously, as you look at that, A sub 10 does not exist because we only have 3 elements in there, and that's 0, 1, and 2. So 10 does not exist, but we don't know that. Python won't know that until we actually run the code. So when we run the code, notice we get an index error. And this is at traceback. So traceback means the program is running. This syntax error, notice we didn't get a traceback because it couldn't run. It didn't actually, or wasn't able to actually run the program. So that's what's called a runtime error. That means at runtime, we get an error. Now, the last type of error is called a logic error. And these are the most insidious. Why? Because Python doesn't know. It just does what you tell it to do. And if you tell it to do something that it understands, it's going to try to do it. Everything could be right. However, what you've done does not solve the logic problem. For example, if I want the midpoint, remember midpoint is, the midpoint formula is M1 plus M2 divided by 2, right? And so let's say I wanted to do something like that, but I accidentally put minus M1 minus M2 divided by 2. Well, Python knows what M1 minus M2 are. So the syntax is correct. It knows how to divide those two. And so it's going to do that and assign it to B. However, that does not solve the logical problem that we're trying to solve. That's why these are the most insidious, because you don't get something on the screen that says, hey, go to this line and fix it, because it's doing everything that you told it to do. So those are the three types of errors: syntax error, runtime error, and then logic errors. So let's go down here and look at this example, this 3D printed statues problem. So this is a problem where I want you to use these 5 steps to actually figure it out. So in this, the problem says you have a single 3D printer and you would like to use it to produce n statues. So you have some sort of formulation that says we need this number of statues, which in this case is going to be assigned to the variable n. However, printing the statues one by one on the 3D printer takes a long time. So if you've ever used the 3D printer, you know it takes a while. So maybe more time efficient first to use the 3D printer to print a new printer. So if it takes that time to print a new printer, now you have 2, but we still have to account for the time that it took to print the printer. But now we can print statues on the 2 printers. That new printer may then in turn be used to print statues or even more printers. Print jobs take a full day, and every day you can choose for each printer in your possession to have it print a statue or to have it print a 3D new printer, which becomes available the next day. What is the minimum possible number of days needed to print at least n statues? So essentially what we're going to do is use these 5 steps to figure out what we're going to do. So must-haves versus like-to-haves. This problem is fairly straightforward. We want to print the minimum possible number of days needed to print at least n statues. So we only have one requirement, and it's a must, okay? Determine the outputs. Remember, we have to work backwards. Our goal is to print the minimum possible number of days needed to print at least n statues. Okay, so that is the output that we are reaching towards. So all of our inputs and the process that we're going to go through is achieving, or is going towards achieving that goal. So let's analyze the inputs. We need to look at the problem to see how we can calculate the number of days needed to print n statues. So what sort of information do we need before we can make that calculation? First, we need the value n. We need to know how many statues we need to print, which the problem tells us is the number of statues that we need to print. This comes directly from the user. They tell us, okay? So remember, they're going to input, or we're going to input n, and that's essentially the only input we need. So in this case, what other information do we need? Well, how much time does it take to print a statue? How much time does it take to print a printer? We know that a statue takes 1 day and a printer. So the statue and the printer take the same amount of time. So let's orient the problem to our environment. So remember, we're using Python to solve this. This means we're giving a full suite of Python constructs, such as if statements, loops, lists, integers, floating point, and so forth. So let's solve the program incrementally. First things first, let's get input from the user. Remember, they're going to input the number of statues they want to print. We're printing whole statues, so we need to input n as an integer. There's no such thing as a fractional statue, so there's no reason to input it as a float. So we have our main, as you can see on the screen here. This is just the standard way that you're going to develop your programs. And if you don't remember why we use the if name, that's, I think, week 3 when we talked about why we use if name equals main. Because remember, Python programs can be executed directly, or they can be imported into another Python program and executed there. Without this, the only way to do it is it has to run from start to finish. So this isn't much yet, but at least we now have all the inputs that the user is going to give us. Now we need to figure out how many statues interacts with our problem. Okay, you can see that we have a choice to make: print statues or print printers. The end goal is to print statues, so we need to see when printing printers is no longer more effective than just printing statues. If we just print printers all day long, we're not actually accomplishing the goal of printing statues. So let's throw everything we have at this problem. We can try all possible combinations. So this is sort of brainstorming right here. What are the ways we can solve this? This is why we're calling it an art. There really is no way where we can say, okay, given this problem, here's how to solve it. It doesn't exist, because that's why you have to sort of have intuition and understand, okay, how do we actually problem solve this? It takes some sort of intuition that says, okay, I understand the problem. Number one, we can print statues, we can print printers. However, as we're printing printers, we're not printing statues, so we're not achieving the goal. But given that we have another printer, we can actually print more statues per unit at a time. So I've drawn out this little diagram. Let me open this, make it bigger here. There we go. So I've drawn out this diagram that shows many different scenarios. So we have 3 different scenarios that I'm showing you here. So on day 1, the printer just prints statues. So it's going to take 5 days to print out 5 statues. That's where n is equal to 5. So on day 0, the printer is just there, and it takes 0 to 1. So it takes 1 day to print a statue. Okay. The second one is second scenario, which is the middle scenario, is we print 1 printer, and then those 2 printers crank out statues. As you can see, day 1 is used to print the printer. And so there is no statues being made on day 1. Then after that, day 2, we have statue, day 3, we have statue, and day 4, we have 1 statue. So it takes 4 days. So as you can see with this problem, if we just keep printing statues, it takes 5 days versus 4 days if we print 1 printer, and then both of those crank out the statues. So as you can see, there is a difference between these 2 methods. And then finally, we have 1 printer prints out a printer, and then both of those printers print out 1 more printer. So we have 4 total printers. As you can see, because we're doing that, it takes 1 day to do the first printer, 2 days to do for both of those printers to print out another printer to give us 4 total. And then on day 3, we can print out 4 statues, but we need 5. So it's going to take an additional day, day 4, to actually give us 1 more statue. Okay. All right, so notice that every time we have a printer to print printers, we double the number of printers that we have. This means we take the printers as a power of 2. 2 to the 1 is 1 additional printer, 2 to 2, 2 squared is 2 additional printers. So we can see that we double the number of printers. If we take the opposite, we have the amount of work that we have to do. Remember, with 4 printers, it took 1 day to print 4 statues. If we only had 1 printer, it would take 4 days. So it's essentially the reciprocal, it's the inverse of that. So in this case, you can see we're going to input the number of statues by converting the input into an int. And then what I do is I have a results list. So basically what we're going to do is we're going to test every possible combination to see which one is the best. And so we're going to store those combinations in the list so we can keep track of which one performed the best. So you can see here what I've done is I've added the total printers that are going to be in here. So we start with 0 additional printers all the way up to n additional printers. Okay, there's no sense in printing more printers than the statues that we need, because that wouldn't make any sense at all. Because if we had 10 printers but we only need 5 statues, well, 5 out of the 10 printers can't do anything because we only need 5 statues. So that's why we go up to n. So total printers, and then what we do is we append the time that is going to be inside of there. Okay, so there we go. We've tested every scenario and we stored the amount of time that it's going to take. Now, once again, we can tell the amount of time it's going to take by actually just stepping through this diagram that I've written and see how long it's going to take to print n statues. And that's essentially what we're doing here. So then what we do is now we have a list of all the different combinations of ways we can do this. We can have 1 printer, 2 printers, 3 printers, that sort of stuff. And we're building up outputs. So now we have all the outputs. We have all the scenarios that are possible inside of a list. And remember, what we want to do is we want to print the minimum number of days it would take if we had this scenario working out to print out the number of statues we want. And so what I do is I take the minimum of all those results, and that will tell us the minimum day that we have. So in conclusion, I know this video is running a little bit long, but in conclusion, solving problems is an art form in itself. I've given you these 5 steps to help you break down a problem into component parts so you can solve one incrementally. Okay, do I know the inputs? Do I know the outputs? Because without that, solving the actual or writing the Python makes no sense. You can't write the Python unless you know, here's what I need to output and here's what I need to input. So there you have it. That is Algorithm Development 101. Thanks for watching.